Harvard University's latest statement today, astrophysicist Avi Loeb continues to draw public attention within the international scientific community. He mentioned an anomalous interstellar object currently under close monitoring in recent multiple lectures, though not granting direct interviews. He confirmed he does not believe the object is a known asteroid or comet. The object's structure and behavior are completely different from all observed objects within the solar system. He likened this phenomenon to discovering an unfamiliar, bizarre object right outside one's front door. He believes the scientific community must maintain both caution and curiosity, especially considering the minute possibility that this object could be an artifact of human technology. Loeb cautioned against dismissing the hypothesis merely because it seems absurd, emphasizing it could represent a black swan event of profound human significance. As debate over this celestial body persists, a startling new development has emerged. On July 1st, astronomers announced a new interstellar object entering our solar system. Preliminary data reveals this object possesses an inexplicably bizarre shape and a wavy orbit. Numerous anomalous signs are under analysis. This discovery has rapidly drawn attention. Researchers are striving to uncover the true nature of this object. Meanwhile, conspiracy theorists continue to fuel its mystique by raising numerous unresolved questions. Currently, Three-Eyed Atlas is steadily penetrating deeper into the solar system, becoming a priority monitoring target for observatories worldwide and sparking a series of new hypotheses that intensify debates over its true origin. Interstellar visitor. Stay tuned for what unfolds next. It will shake your very soul. If you're captivated by the enigma of Three-Eyed Atlas and yearn to witness more breathtaking cosmic tales, please click the like button. Let the universe know you're watching. Every click fuels the journey to explore unknown life. Leave a comment. Tell me where you're watching this video. I want to see which corner of the world is witnessing this. Join me. On October 3rd, as China's Tianwen-1 orbiter approached Mars, it unexpectedly captured the first image of an interstellar object through its high-resolution camera system. Though blurry, these images are monumental. Humanity's first glimpse of an interstellar comet originating from another planet. This visitor unveils a new perspective from beyond our solar system. Preliminary data indicates Tianwen-1 observed the object 29 million kilometers from its target. The images reveal a bright, compact comet nucleus enveloped by a dense, diffuse gas layer spanning thousands of kilometers. For typical comets, this structure arises from ice and dust sublimating under sunlight. However, the scene recorded by Tianwen-1's camera deepens the mystery. Surface features and the gas halo surrounding the object both show significant deviations from known cometary models. Despite its modest 38.7 centimeter diameter, far smaller than NASA's high-performance telescopes, the Tianwen-1 camera possesses sufficient sensitivity to capture faint brightness variations and peripheral structures. These fluctuations suggest potential localized activity such as jets or outflows originating from the comet's nucleus. Despite the immense distance and the target's extreme faintness, these details remain clearly visible. The emergence of this image set represents the most captivating observational achievement of an interstellar celestial body to date. Anticipation within the astronomical community has reached a fever pitch. NASA's Mars Reconnaissance Orbiter is poised to release clearer imagery via its high-resolution camera. Equipped with a 50-centimeter primary mirror and exceptional imaging capabilities, these images could be transmitted at any moment. They are expected to reveal a three-tailed structure and a side view of the countertail. Unprecedented perspectives may reveal internal structure, ejection systems, mapping outflow gas streams, even narrowing the range of speculations on the nucleus's size and shape. If all goes as anticipated, this will become humanity's most comprehensive dataset ever obtained from an extraterrestrial visitor. But to grasp why the upcoming observations are critical, one must revisit what existing data has already revealed. A series of anomalies defy explanation by traditional comet models. It is precisely these ambiguous yet contradictory signals that leave scientists holding their breath in anticipation of whether high-resolution new imagery will unravel the mystery or continue to propel the Three-Eyed Atlas into the realm of scientific and theoretical debate. The landing site remains undetermined. The most striking and controversial feature eye-like images are directly related to orientation. Cometary jets consist of elongated, bright bands of material radiating outward from the nucleus. In typical comets, when the nucleus rotates, these jets often appear blurred or distorted in long exposure images, forming curved or diffuse trails. Nuclear rotation disperses the jets, causing them to lose their sharp form. Yet the three-eyed comet's imagery completely defies this pattern. In long-exposure composite analysis images from early November 2025, its jets appear as narrow, straight, and stable bands of light extending over 1 million kilometers into space with no signs of rotational blur. This makes the object appear stationary or suggests the jets remain stable, unaffected by rotation. The anomaly grows increasingly pronounced. Compared to the three-eyed star chart measured earlier this year was approximately 16 hours at the comet's ejection rate of hundreds of meters per second. The material forming the jet would require nearly a month to traverse this distance as shown in the progress images. During this period, the nucleus could complete dozens of rotations, enough to twist the jet into complex spirals or diffuse patches. Yet the jet remains perfectly aligned, exhibiting almost no oscillation. This phenomenon quickly became one of three core enigmas. Comet Eye Gallery directly challenging all standard comet models. If the jet were solely produced by solar radiation heating acting on surface volatiles, it should exhibit dynamic variations with the nucleus's rotation and changing illumination. Yet the observed extraordinary stability suggests other mechanisms. Perhaps a continuous outflow or some non-gravitational directional axis. The jet's sharp linear structure further reinforces internal processes such as magnetic field alignment, enclosed jet channels, constraints within the comet nucleus's fractal structure, or complex surface dynamics. Beyond scientific historical observational records, regardless of the ultimate explanation, this phenomenon constitutes one of the three core enigmas, one of the solar system's most enigmatic objects. Beyond its anomalous jets, triple-eyed Atlas's other characteristics add to its mystique. Its retrograde orbit traverses the solar system, and this retrograde motion is key. As it crosses the solar system, triple-eyed Atlas always moves in the opposite direction to the planetary bodies. Surprisingly, however, its orbital inclination relative to the ecliptic plane differs by only a few degrees. Statistically speaking, such near-perfect alignment cannot be attributed to mere chance. This alignment also makes B303 Atlas an ideal target for observing Earth and Mars, yet it poses a significant challenge. How could an object formed deep in the cosmos eventually enter the solar system along such a precisely aligned plane? This has prompted many researchers to consider unconventional scenarios, from gravitational perturbations to ancient collisions to the influence of unknown mechanisms within the interstellar medium. Initial spectral analysis adds further intrigue. Data reveals Atlas's nickel-iron ratio diverges significantly from typical cometary composition with exceptionally low water content. These clues suggest the object may originate from a radically different protoplanetary environment, perhaps a region where icy resources depleted during formation, or a stellar domain where metallic condensation occurred under unique thermal conditions. Its anomalous chemical composition, combined with its retrograde orbit and high-speed traverse through interstellar space, make Atlas III a candidate celestial body potentially carrying material from ancient planetary systems. Temperature gradients and chemical environments may be completely opposite to those in the solar system. This makes each new measurement not only an observation of a peculiar object, but also an opportunity to reveal the distant history of an unknown world. Tianwen-1 imagery, though still limited in clarity, they provide crucial clues revealing the light distribution patterns of the triple-eyed star map and the inferred morphology of its gaseous cloud and stellar core. Diffuse light indicates ongoing eruptions, but overall dimness suggests a comet with relatively small active surface areas. This indicates the stellar core may be extremely dense and compact, only hundreds of meters wide, with activity concentrated in localized regions rather than uniformly distributed across the surface. Nevertheless, U.S. experts emphasize that Tianwen-1's data merely lays the groundwork for subsequent analysis. Researchers anticipate breakthrough discoveries from an upcoming series of observations utilizing the high-altitude camera on NASA's Mars Reconnaissance Orbiter. Equipped with high-resolution instruments and sensitivity, It has yielded numerous major planetary science discoveries. From its orbit around Mars, the high-altitude camera captures rare side-view images, including comet tails and ant tails, particularly in the southern polar region, often producing striking visual effects when observed toward the Sun. Due to the influence of dust orbits and radiation pressure, this structure is frequently misinterpreted. American scientists hope new data will reveal this phenomenon with precision far exceeding previous observations. Its anticipated resolution will reach approximately 30 kilometers per pixel. This high-resolution camera will enable detailed mapping Comet Atlas along its dust and gas tail system with sufficient precision to determine whether outgassing originates from multiple active regions or a continuous surface flow network. This is precisely the crux of American researchers' focus, which may fundamentally rewrite our understanding of this interstellar object's dynamic properties and fundamental nature. Global attention is focused on Comet Atlas. The American scientific community holds high expectations for NASA's observational results, renowned for their reliability and scientific value, which will play a pivotal role in deciphering the true identity of this mysterious visitor from beyond our solar system. However, the release of images has encountered unexpected delays due to complex bureaucratic procedures. Backlogged data processing and recent governmental upheavals have both slowed the release process. Scientists directly involved in the project have stated the data is ready and complete, awaiting only official clearance for release. The prolonged wait has fueled speculation about what the images might reveal, ranging from purely scientific details to bold hypotheses about the true nature of the three-eyed atlas. For the astronomical community, the three-eyed atlas presents both a unique challenge and a rare opportunity. The celestial body's orbital path does not fully align with existing comet models, forcing researchers to continually re-examine their fundamental theoretical assumptions. Yet this anomaly also presents an unprecedented opportunity to expand humanity's understanding of interstellar matter. B3I Atlas Earth and Mars observation diagrams signify humanity's possession of dual observational space laboratories. This is virtually unprecedented. Unlike previous interstellar objects, those bodies were either too small or moved too swiftly or exhibited insufficient activity, making in-depth study difficult. Oumuamua, however, has demonstrated sufficient activity to generate clear signals while maintaining stability over extended periods. This enables both ground-based telescopes and high-tech orbital observation equipment to continuously track and measure its evolutionary process, with each observation cycle lasting months. With this rare observational capability, Oumuamua has become an ideal research subject that may reveal the structure and composition from deep space. Some scientists have begun comparing three anomalies of Oumuamua with a previously sensational interstellar object. The first anomaly, Oumuamua exhibits anti-gravitational acceleration, yet displays no visible coma or outgassing activity. Its anomalous trajectory and seemingly silent appearance have sparked years of debate and even theories about its possible artificial origin. Velt 2 Borisov. Its morphology closely resembles a typical comet. Yet it possesses an anomalous high velocity. Its dust content far exceeds scientists' expectations for interstellar objects. In this case, the three-eyed star is becoming a hybrid of two worlds. It exhibits the typical ejection activity of a standard comet, while simultaneously possessing characteristics difficult to reconcile with traditional natural models. Such as reasonably aligned jets, an unusually flattened retrograde orbit, an anomalous chemical composition and activity levels inconsistent with its predicted size. All these factors make Oumuamua an unsolved mystery. Science has yet to find a solution. The combination of seemingly familiar behaviors and highly anomalous signs has excited many researchers. Some view it as an opportunity to gain deeper insights into the nature of interstellar matter, but others believe Oumuamua may hold the key, the enigma left by Oumuamua and Borisov. While awaiting the latest high-resolution data, the scientific community continues close monitoring. hoping that Atlas III will become a turning point in humanity's understanding of these mysterious interstellar visitors. Should subsequent high-resolution images confirm that Atlas III's jets indeed maintain stable orientation during rotation, this would constitute a discovery of profound significance. Such a scenario could imply the existence of internal coupling mechanisms such as localized magnetic fields capable of guiding outflowing material to lock its rotation to the stellar core, or internal mass redistribution effects, stabilizing the jet axis in ways not yet accounted for by traditional models. On the other hand, this phenomenon could also be due to geometric conditions. On the other hand, this phenomenon could also be merely the result of favorable geometric conditions, namely, the comet's rotation axis coincidentally aligns with the jet direction, leaving the jet unaffected by rotation, creating an illusion of absolute stability. Regardless, this discovery will compel scientists to reassess the formation and evolutionary mechanisms of cometary jets, particularly for comets born in environments beyond the solar system. Beyond deciphering jet behavior, new data may also reveal the physical state of stellar cores. If the outflow indeed exhibits a narrow, straight, and highly collimated morphology, it implies the stellar nucleus must possess a robust, rigid outflow structure to channel gas along a fixed direction. Such structures require more cohesive material than the porous, brittle comets commonly found in our solar system. Conversely, if high-altitude images show the outflow diffusing or fanning out, it may indicate a highly fragmented surface undergoing rapid erosion by solar radiation. Conversely, if high-altitude images show the jet diffusing or fanning out, it may indicate a highly fragmented surface undergoing rapid erosion by solar radiation. Both scenarios provide key clues to Comet 3H Bear's origin and the type of environment in which it formed. Regardless of the outcome, the forthcoming data will undoubtedly play a pivotal role in reshaping our understanding of interstellar material evolution. Another major enigma that captivates both scientists and conspiracy theorists lies in the remarkably stable, light curve of the three-eyed Atlas comet. Photometric measurements reveal only slight fluctuations in the object's brightness, despite its continuous rotation and the ever-changing angle of sunlight, which alters illumination intensity across different surface regions. Yet the brightness curve remains nearly flat, an extremely rare phenomenon among active comets. Typically, gas outflow rates vary regionally, causing periodic brightening and dimming, reflecting the rotational state of the stellar nucleus. Yet 3I Atlas maintains astonishingly constant brightness, suggesting its active regions may be symmetrically distributed across its surface, causing brightness variations that nearly cancel each other out. More radical hypotheses point to some global mechanism such as internal heating or an intrinsic energy source driving the object to eject gas uniformly. This accelerated rotation sparks extensive speculations. Some observers question whether 3I Atlas's peculiar stability maps to some complex energy regulation mechanism uncommon in nature. They cite the control behavior of jet aircraft as an analogy, a hypothesis proposed by a study. Oh my goodness, does 3-eyed Atlas possess some thermal regulation function or an energy distribution system? We cannot yet imagine. Or is this merely a geometric coincidence meticulously orchestrated by natural physics and structure hundreds of millions of years ago? Though scientists still favor natural explanations for 3-eyed Atlas's astonishing stability, its light curve continues to cultivate fertile ground for bolder hypotheses until advanced data is released. The unknown void will become the birthplace of rigorous science and the wellspring of conspiracy theories. Astronomers are particularly focused on the interaction between the triple-eyed star chart and the solar wind as it traverses the heliosphere. This environment is saturated with high-energy charged particles capable of bending, stretching, or even completely distorting a comet's tail while generating plasma radiation phenomena that envelop celestial bodies. For interstellar objects that have not undergone solidification processes within the solar system environment, such as primordial comets, such interactions become more unpredictable and of greater scientific value. By analyzing the morphology of the comet tail and its orientation relative to the Sun, researchers can gain insights into the delicate equilibrium between solar radiation pressure and the stream of particles escaping from the stellar core. A sharply bent reverse tail may indicate dust ionization and entrapment within magnetic fields. If it maintains a distinct linear structure, the dust flow may be driven by non-thermal repulsive forces or influenced by isolated plasma phenomena, particularly 3 I-star charts traversing the heliosphere. At speeds far exceeding typical comets, function as natural probes, revealing dust and gas particles under the harshest solar wind conditions. Some analysts even speculate that the anomalous behavior of the reverse tail may reveal previously unrecorded interaction patterns such as abnormally highly charged dust or unresolved intrinsic magnetism within these minute celestial bodies. These data not only deepen our understanding of 3I Atlas's operational mechanisms, but also open doors to directly study plasma effects in interstellar space, where objects are governed by fundamentally different force fields than those on Earth. Thus, 3I Atlas continually surpasses scientific expectations. Many ponder whether this towering tail structure will ultimately serve as empirical evidence for natural phenomena, or continue to fuel controversial theories. Debates surrounding this enigmatic visitor have persisted for years. The forthcoming high-precision data may also reveal subtle asymmetries in the dust tail of 3I Atlas, which could reflect rotational torque or indicate fluctuating activity over time. Should new imagery show signs of fragmentation, such as isolated bright spots, discrete clumps of material, or even secondary cores, it could suggest the triplet nebula is entering a phase of structural disintegration, gradually fragmenting under the influence of thermal radiation pressure. This would provide rare direct evidence revealing how interstellar objects endure solar thermal radiation and respond to environmental changes. It will never evolve to adapt, revealing its mechanical properties and material strength at high resolution. If present, these features would be hard to hide. Minor asymmetries within its slowly rotating dust stream, or among its fragmented debris, may prove crucial in determining whether 3I Atlantis is merely an ancient disintegrating comet or an object with an unknown structure. Even if the phenomena revealed by the data exceed expectations, they may fuel further conspiracy theories speculating on the celestial body's mysterious origin and nature. In the near future, when high-resolution images are released, we may realize that this latest interstellar visitor, 3I Atlas, not only carries dust particles from distant planetary systems, but will also unveil the next modern mystery, one that may remain unresolved for a long time, keeping both the scientific community and the American public engaged in exploration for years to come. Don't forget to subscribe to the channel to continue exploring the mysteries of space. See you next time.